Welcome to a lesson that will prove why the integral of 1 divided by x dx equals natural log absolute value of x plus c. More specifically, why does the antiderivative have the absolute value of x in it? To begin, we might be thinking, because we know the derivative of natural log x equals 1 divided by x, it must follow the integral of 1 divided by x dx equals natural log x plus c. While this isn't wrong, the domain for y equals 1 divided by x is all real numbers except 0, and the domain of natural log x is x greater than 0. We'd prefer to have an antiderivative that has the same domain as the integrand function. So while this is true, it's only true when x is greater than 0. Before we get to our proof, let's look at this graphically. Let's first graph the original function of y equals 1 divided by x. Notice the domain is all real numbers except 0. And now let's graph the function y equals natural log absolute value of x from the antiderivative formula. Notice when we graph this function, the domain of this function is the same as the domain as the integrand function. And if we graph just y equals natural log x, notice the domain is only x greater than 0. The reason this matters is, if we wanted to use the fundamental theorem of calculus and evaluate the definite integral of 1 divided by x, let's say from -4 to -1, we wouldn't be able to use the antiderivative of natural log x, because if we tried, we get the natural log of -1 minus the natural log of -4, and -1 and -4 are not in the domain of the natural log function. However, if we use the antiderivative natural log absolute value of x, we can evaluate this definite integral. We get natural log absolute value of -1 minus natural log absolute value of -4, which equals natural log 1 minus natural log 4. And now let's get to the proof. We'll consider two cases. We'll consider when x is greater than 0 and when x is less than 0. And now we'll integrate using substitution. For x greater than 0, we will let x equal e to the t, because e is positive. Notice e to the t is always going to be greater than 0. And now we find dx, where dx equals the derivative of e to the t with respect to t times dt, giving us dx equals e to the t dt. And now I perform substitution into the original integral. We substitute e to the t for x and e to the t dt for dx. E to the t divided by itself simplifies to 1, and we get the simple integral of the integral of 1 dt, which is equal to t plus c, the constant of integration. But we want the antiderivative with respect to x, not t. So now we need to go back up to the equation x equals e to the t and solve for t. To do this, we will begin by taking the natural log of both sides of the equation. This gives us natural log x equals natural log of e to the t. And now we apply the power property of logs to natural log of e to the t, which gives us t times natural log e. Natural log e is equal to 1, giving us t equals natural log x. And therefore, the antiderivative with respect to x is natural log x plus c. But again, this is true only when x is greater than 0. So now we'll consider the second case where x is less than 0. Because x is always less than 0, we will now let x equal negative e to the t, which is always going to be less than 0, giving us dx equals negative e to the t dt. And now I perform substitution again. X equals negative e to the t, dx equals negative e to the t dt. Simplifying, negative e to the t divided by itself simplifies to 1. We have the same simple integral of the integral of 1 dt, which equals t plus c. But now we need to go back up to the equation x equals negative e to the t and solve for t. Let's first multiply both sides of the equation by -1. This gives us negative x equals e to the t. Next, we take the natural log of both sides of the equation. Natural log of negative x looks strange, but remember x is less than 0, and therefore negative x would be greater than 0. Applying the power property of logs to natural log of e to the t, we get t times natural log e, which gives us t times 1, and therefore t equals natural log negative x. And therefore, when x is less than 0, the antiderivative is natural log negative x plus c. Notice we have two antiderivative formulas for the integral of 1 divided by x dx. However, if we notice, the input for natural log is x when x is greater than 0, and negative x when x is less than 0. This should remind us of the definition of the absolute value of x. The absolute value of x is equal to x when x is greater than 0, or positive, and the absolute value of x equals negative x when x is less than 0 or negative, which means we can combine these two antiderivative formulas and say the integral of 1 divided by x dx equals natural log the absolute value of x plus c. I hope you found this helpful.